You might notice that my title here is a little bit different than the one she just read. I want to be abundantly clear that the work that I did here, while it was set up in the framework of the Viper mission, any vehicle, lander, rover with an inertial measurement unit, or it is just an accelerometer, kind of like you would have in your car, just space grade. Any mission that has one of these things can be used for seismic instrumentation as kind of a direct answer to Dr. Prem's question yesterday. So, how do I do this? There we go. So, an inertial measurement unit is a triaxial accelerometer. So it collects data on acceleration in the X, Y, and Z directions, which is functionally the same thing as a seismometer, as the thing that is in your car that tells you how it's accelerating. These are just space hardened. The standard one that NASA uses for most of its mission is the Northrop Grumman LN200S. We do not have access to that, so instead we are using just a commercial grade $50 one that you can get on Amazon. And while Viper at this stage may or may not launch, this is applicable not only to Endurance A, which has an extremely long rover traverse planned or proposed, in addition to Prime 1, which in addition to having the Trident drill, which was supposed to fly on Viper, does have an IMU, and as well, the Cadre set of rovers will have IMUs. And the fact is that drills don't go very deep. Trident is, as far as I'm aware, the deepest drill that we have access to for spaceflight, and that only goes to about 1 meter. Any sort of volatiles, maybe ore deposits, other targets of interest are very likely to be found deeper than 1 meter in the soil or in the regolith. So looking deeper than that is going to require some sort of geophysical exploration. So the theory here is your basic seismic active seismology theory, and that can be described as the convolution of 4 different responses. So that's the source response, which is that actual function representing a hammer strike, percussive drill function, the rotary function, what that actual source of energy that is injected into the ground looks like. The rover response, so how does that rover vibrate? Does it have resonant frequencies? What is its response to that source? How does it vibrate as it's driving over the surface? The ground response, so in the end, the ground response is going to have that information about the subsurface that we ultimately want to extract. And the instrument response, what is its noise floor? Does it have bit drops? What are its idiosyncrasies as an instrument itself? And the source, rover, and instrument responses are experimentally categorizable prior to flight. But IMUs have not been used in a seismic experiment before. And so our research goals here are primarily, first of all, to understand the performance of an IMU as a seismic instrument, and as well as experimentally quantify source and rover response before launch. Initially, this was Viper source and rover response, but we're now broadening this to understanding how one would actually extract a rover and source response for any mission that you might want to apply this scientific method to. So the first order of business was comparing an IMU versus traditional seismic instruments. So we use this commercial grade Witt Motion SINDT TTL IMU, which collects at 200 hertz and has a sensitivity to ground motion of 50 millimeters per second squared. A standard geophone or nodal seismometer is going to collect at much higher frequency, and the frequencies of the ones we used here are on the screen. Seismic instruments traditionally can detect somewhere in the vicinity of a nanometer per second squared. So we're talking orders of magnitude difference in ground motion sensitivity. So we placed all 3 instruments as close as possible together on volleyball sand court, which is the closest approximation locally that we had to lunar regolith analog. And we used percussive impulse that was 3 joules. And you can see here the results of the same strike on all 3 instruments. So you can notice on the IMU that this spectrogram is much lighter than the other 2 spectrograms. That means that the noise floor here is going to be a lot higher. So as we would expect, since the sensitivity to ground motion of the IMU is only going to be like 50 millimeters per second squared, you would expect that noise floor to be much higher. The geophone is the only source that actually resolves the entire source function of the rod drop. It gets aliased, so kind of the resolution isn't full. We don't see all the components of that strike on the nodal seismometer, and we really see very little of that on the inertial measurement unit, but we do see that very strong amplitude. And there is a little bit of a difference in amplitude in the beginning versus the middle. So we can see that there is an ability for the IMU to capture difference in magnitude as a strike continues. We then took the IMU to an analog site and struck a bit of basalt as well as some tuff as the regolith analog. And you can see very clearly, there. So the basalt is going to have a very high peak. There is very little attenuation. We can see that source kind of clearly. It's still aliased as it was, as you saw on the previous slide. But you can also see that in the tuff, that magnitude does not get as high, and that energy is much more spread out. It's much more attenuating, which is exactly what we would expect to see given a higher resolution seismic instrument. And in my opinion, that is even clearer to see. You have this very high magnitude, bright, narrow strike on the basalt, whereas you have this very mushy, attenuating data on the tuff. So it is very clear which of what kind of material you're looking at in terms of how solid it is versus how attenuating. So our preliminary conclusions here. Our source and ground response are going to be time aliased. So actually getting arrival times to get precise seismic wave velocity is going to be very difficult on a rover-based IMU seismic experiment. However, relative amplitudes are going to be going to be able to be studied, as well as that coda and attenuation. And you can see here, so if you have a very high dispersion and attenuation material with loose regolith, you're going to have a very small amplitude signal here. Whereas if you have a solid ice layer, something reflecting a lot of energy, that amplitude is going to be much higher. Versus if you have kind of intergranular ice that acts as kind of a concretion, you'll maybe get something in the middle of the road here. We also did some Trident field tests, but I didn't want to run over time. Please ask me if you would love to see that field test data. I have that in comparison to an approximation of the response of the Curiosity IMU. So actual data that we have approximated, I guess. How do we characterize the rover response? So are we going to want to get resonant frequencies when we do vibration tests for launch, or is there going to be a better way to actually understand that rover response? Are we going to need to do other types of testing? Is that rover response going to be consistent over space and time? So I think of Curiosity's rover wheels falling apart. Is that going to change how the rover responds? Is accumulation of regolith or other dust on the rover going to change how it vibrates that rover response? And then ultimately, can we resolve the ground and background response using injected energy? While we do think that we're going to be able to extract some ground response, it's not going to be at the same level as, say, InSight, but there is going to be scientific data that we can extract. And in especially engineering demonstration missions, I know there's concern about the scientific value we can extract from some of these, that it has been expressed that the scientific value for geologists is of concern for some of the technology demonstrations on the CLIPS missions. This is something that we should be able to get a decent amount of information and some constraints that we would not otherwise have using this inertial measurement unit. And with that, I would like to hopefully get us back on schedule. Thank you so much.